Hello everyone, I am Dayanand Jadhavar, Chemical Engineer and Senior Manager, Production. Welcome to this training on limiting oxygen concentration, commonly called LOC, and oxygen requirement for fire and combustion. In chemical plants, we handle many flammable solvents, vapors, gases, dusts, and oils. So understanding oxygen control is very important for fire and explosion prevention. LOC means the minimum oxygen concentration below which combustion cannot be sustained. In simple words, if oxygen is maintained below the LOC, fire or explosion cannot continue, even if flammable vapor and ignition source are present. Now let us understand the fire triangle. For fire, three things are required: fuel, oxygen, and heat or ignition source. Fuel may be solvent, vapor, gas, dust, or oil. Oxygen normally comes from air. Normal air contains around 20.9% oxygen by volume. Ignition source may be spark, static charge, hot surface, welding, friction, or electrical fault. If any one element is removed, fire cannot sustain. LOC works by controlling oxygen through nitrogen inerting. Now let us understand LEL and UEL. LEL means lower explosive limit. Below LEL, the mixture is too lean to burn. UEL means upper explosive limit. Above UEL, the mixture is too rich to burn. Fire or explosion risk exists when vapor is between LEL and UEL, oxygen is above LOC, and ignition source is present. For example, methanol has approximately 6% LEL and 36% UEL. So between 6% and 36%, methanol vapor can form a flammable range if oxygen and ignition are available. Some important fire properties are flash point, fire point, auto ignition temperature, and minimum ignition energy. Lower flash point means higher fire risk. Auto ignition temperature tells us when material can ignite without spark. Minimum ignition energy shows why static charge can be dangerous. Approximate LOC values in nitrogen atmosphere are: methanol, 8 to 10% oxygen; acetone, 9 to 11% oxygen; toluene, 9 to 10% oxygen; acetonitrile, 10 to 12% oxygen. Actual LOC depends on solvent, inert gas, temperature, pressure, and test method. Therefore, always keep a safety margin. Now let us discuss nitrogen purging calculation. Nitrogen purging reduces oxygen inside reactors, tanks, receivers, dryers, centrifuges, and pipelines. For dilution purging, formula is C equals C0 times e to the power of n. Where C is final oxygen, C0 is initial oxygen, and n is number of vessel volume changes. For example, to reduce oxygen from 20.9% to 7%, required volume changes are approximately 1.09 vessel volumes. For a 10 cubic meter vessel, theoretical nitrogen requirement is about 10.9 cubic